Hello there. In this video we're going to talk about sine waves and phasors. And so at first let's kind of just refresh our memory about what's going on with the sine wave. Now if I were to give you an example of a three-phase system, we could see that we've got voltage sine waves that are out of phase with each other, one for each phase. And they're about 120 degrees apart. And what ends up happening is you have this big sort of mess of sine waves, and this is just voltages. So if we were to go ahead and plot on top of this currents, we'd see that we've got basically sort of an unrecognizable mess of things, and it becomes to be way too much to sort of take a critical analyzation of what's going on in that system. So if I were to, ask you, what's the comparison of this to that, you'd start to get lost, and you really wouldn't have a good feel for what's going on in that system. It's too much. It's way too much. And what we want to do is be able to compare those voltages and those currents, so we do need all that data. So what is it that we got to use instead of a sine wave graph? And that is our phasors. So if we have a look, a phasor is a simplified version of a sine wave. Now we know that a sine wave can have an RMS value, root mean squared value. If I had to just kind of draw a simpler version down here, if we have a 120 volt source, we have an RMS value of 120 volts. Well, that means our peak is 170 volts roughly, but really the RMS value is it's the effective voltage, the DC voltage equivalent. So this is what we care about most of the time, is the RMS voltage. So when we go ahead and we plot phasors, we're going to use the RMS voltage and just have the magnitude of the phasor, meaning the length of the phasor, equal to the RMS voltage. So that would be 120 volts. So that's first part of the phasor, is the length is going to equal the RMS value. Okay, so if it's current or voltage, it will be RMS voltage or RMS current. Now, that is the one part, the length. The other part is the angle. So why do I have an angle here? And if I were to compare that to a voltage phasor that's down here, say it's equal to 120 volts, and that's equal to 120 volts, and yet why am I drawing them at different angles? What's going on here? Well, the other part to the phasor is basically the phase shift in our sine wave. So it's time. It's the time in which things happen. We can see that this sine wave here peaks, and then this sine wave over here peaks, and then this sine wave over here peaks. And the further we go in this direction, in this big mess of sine waves, more time has elapsed. So if this happens first, and then this stuff, and then this stuff, and it kind of works its way across. And so when we convert it to a phasor and we try to understand the system, what we have to do is we just pick a reference point. We say this is 0 right here. So we'll have a 0 phasor. And we're going to measure all of the other phasors from that point, so we can see that this phasor here is behind this phasor, which is behind that phasor. If I have something over here, it would actually be ahead, because it's happening first, and then here, and then here, and then here. And you can see that things start to get really, really messy, really, really quick on there. So that's what we're doing here. We've got our reference angle, which is where we're going to put it at 0 degrees. And we're going to measure everything else, whether it is leading, which is ahead, which means it happens before. So this is our lead. Or if it's lagging behind, and it's happening after the fact. So we've got leading over here, and we've got lagging over here. So it takes more time for this to happen, and this has already happened by the time we have got to our reference point. And the reference point is just something we just called it what it was. We just picked a point and we went with it. Most of the time we'll have a reason for why we pick it, but it doesn't really matter. If I change the reference, all it's going to do is shift the entire drawing to a different moment, and this becomes my reference, and these phasors come up this direction. Okay, so that is what's going on with a phasor. It is a magnitude measured in RMS, and it's the time in which it happens compared to that reference. Okay, so in this I've got 3 different voltages. I've picked this, my reference, in the middle at 0 degrees. I've got one that's a little bit ahead, so it already happened by the time I got to my reference peak. And this one has lag behind, meaning it has happened after my reference peak in my sine wave. Okay, so I've only got 3 on here. If we were to look at something like 3-phase, we could have phasors everywhere, and you could start to see that if I were to try and plot this on a sine wave graph, it would be just an unreadable mess. So phasors happen to be one of the most useful things to us when we're calculating our power in terms of voltage and current and when they're happening, because now we've got this sort of time domain as well. All right, so this was a brief intro into sine waves comparing to phasors, and in the next video what we're going to do is break apart a phasor and see what its components are and how to add phasors together. All right, so I'll see you in the next video.